This is part 2 of the parametric and vector video. I want to show you something on the graphing calculator here, since you do need to be able to be comfortable doing parametrics and vectors on the graphing calculator. So let's go back to here where we had our normal y equals f of x notation and our parametric equations for the same exact curve and same scenario, just different way of expressing it. I'm going to go here and I'm going to go to y equals and type in my normal function notation, y equals f of x. Now for the window, x here is on the ground, so I went from -1 to 30 and then -10 to 55 because I started at a height of 50, and I graph it here. Now notice my window as well. My x scale is 10 and my y scale is just 1. So you might be thinking, well, this isn't the position of the cart because the cart didn't go up at first. But keep in mind that for our scenario, we assumed that when x was 10, that was the edge of the cliff when the cart started going down. So here x is 10, going up, that's at 50. So this is right when the cart started going off the cliff, like that. Now I want to show you how to graph parametric. We're going to do the same exact thing. And you go to mode here, and you're going to go over to parametric. We will do polar next. Notice polar is right next to it, so hit enter. As soon as you go to y equals, you have the parametric notation. So I'm going to type in the x and the y equations parametrically, and then when you go to the window, you have to be careful. You have to specify a scale for your time. So like, how many seconds do you want this to be valid for? My x is the horizontal and my y is the vertical. So I'm going to hit graph right now, and this is the exact part or motion of the cart. And notice that it starts like right in midair here, because that's whenever time is 0. The cart is just going off the cliff. And notice my equation keeps going past the ground. You can adjust your time parameter however you wish. Like, let's say I wanted to say, if I were to go backwards 1 second in time, it would include this upward part of the motion, which didn't really happen. Or let's say I wanted to restrict it and say, I only want to see the times when the cart is actually moving, like the realistic times. We didn't solve for whenever the cart hits the ground, but it's about 3.1 something. So oftentimes with parametrics, you're going to restrict the time so that the path or the curve is only valid for what you want happening in your motion. So you have to be comfortable adjusting your window and typing into here. So this is the path we were looking at. What I'm going to do now is show you a couple examples so that on Monday and Wednesday you can hit the ground running here and do some problems. So let's start by eliminating the parameter for a slightly more interesting problem here. That's not just basic solving for t and substituting into the other equation. Let's say I were going to solve or try and solve for t in my x equation and substitute in for t here. That's what I did before, and it went pretty well. I'd be doing x plus 1 divided by 2 equals cosine of t. Well, in order to solve for t, I'd have to do cosine inverse of each side, and I feel like plugging cosine inverse into here would be really ugly. So let's try doing something else. Let's try solving each of these for sine and for cosine. And then let's plug into our trigonometric identity, which says sine squared, this time it's of t, plus cosine squared equals 1. That's the first and most well-known Pythagorean identity. So I'm going to take whatever sine is equal to, which is y minus 1 over 3 squared, plus cosine of t, which is x plus 1 over 2 squared equals 1. Notice that this is x and y notation. You could solve for y to make it look like the y equals f of x you're more accustomed to, but we have eliminated the parameter t. We just have a function, x and y. Now actually I can't even call this a function, because if you were going to graph this, this would actually be an ellipse. Now, I know we haven't done too much with ellipses. In fact, we haven't talked about them at all this year. I don't know if you saw them in pre-calc. They're like a stretched out circle. The equation of a circle is this guy right here. This can't be a circle. It's called an ellipse because x's and y's don't have the same width from the center. It's more stretched out vertically this time because for y, the denominator is bigger. But anyway, this is how you eliminate the parameter here. A little bit of a different type than the other one that you saw. So pre-calc trig identities coming to the rescue. Now let's take this problem, which is really, really common. It's almost always one of the parts of a free response. And it's going to ask you, all right, this is x and y here, x of t, y of t. Find dy dx in terms of t and find the equation of the tangent line. So we're still doing tangent lines. It's still the same exact method that we've done before. And I'm going to find dy dx in terms of t. So let's go to our formula sheet here. And to find the slope of a line, or slope of the path of the parametric equation, I should say, you have to do dy dt over dx dt. So I'm going to recopy that here. So this is part A. Dy dx equals dy dt over dx dt. Now just keep in mind, think of your fractions here. To divide two fractions, you multiply by the reciprocal of the denominator. Oh wow, this should be an x. Right here. Eek. Okay. Anyway, think of fractions you multiply by the reciprocal of the denominator. Your dt's cancel, leaving you with dy dx, which is why this equation even works. So I need to take my derivative of my y divided by derivative of my x. So my dy dt and my dx dt I'll do over here, so it's not a mess. Dy dt is the derivative of this, which is 3. Oh my god, I'm doing the wrong problem. Hold on. So dy dt is the derivative of this with respect to time, so that'd be 3t squared minus 2t. Dx dt is the derivative of my x, which would be 2t plus 1. And all you have to do is put them over each other. So 3t squared minus 2t over 2t plus 1. This is the slope on a parametric curve at any time t. One thing I want you to realize is that dy dt and dx dt on their own have nothing to do with slope. Dy dt is the instantaneous velocity in the y direction. Dx dt is the instantaneous velocity in the x direction. Only whenever you make a fraction out of them. This has to do with slope of a tangent line. These individually do not. So now I have to finish in order to find my tangent line. So I have to find the slope at that specific point. So dy dx at t equals 1. I'm going to plug 1 in. I meant to say we have to plug 2 in because we want to know this equation of the tangent line when time is 2. So I'm going to take my equation for slope, which I just found, and I'm going to evaluate it at 2. Here's my slope, 8/5. Now I need a point as well. So they give me a time. In order to get a point xy, I have to plug into both my x equation and y equation separately. I end up with the ordered pair 5, 4. So at time equals 2, I'm at 5, 4. So my tangent line is y minus y1 equals mx minus x1. Examples 3 and 4 are other things you'll see very often. They're pretty quick examples. They're nothing too difficult. Sometimes they're going to give you the position written like this, where you have to know that the first one is x of t, the second one is y of t. Sometimes they're going to write them out separately like this. So if they give me the position vector, which oftentimes is called s of t, we want the velocity vector. Now keep in mind that when they say find the velocity, you're still going to have a vector. If they say speed, that's magnitude, you're just going to get a number when you plug in. Acceleration is another one where you end up with a vector. So I'm going to use both of these. So velocity is, this should be a prime right here. Velocity is x prime, y prime. Acceleration is x double prime, y double prime. So that makes sense, so it's not too difficult here. A lot of times you're going to see a v hat, it's called. That little thing here means a vector. So I need the derivative here. So 1 over t squared plus 5t times the derivative of what I'm doing the natural log of, comma 6t. Now I want the velocity at times 2, so all you're going to do is plug 2 in. 2 times 2 is 4, plus 5 is 9, 2 squared plus 5 times 9 is 14. And then when I plug 2 in here, I get 12. So this is your final answer. And keep in mind, we plugged into this equation right here. Now to find an acceleration vector given my positions, what I'm going to use is this formula here. So I'm going to find the second derivative here. So x prime would be 5t to the 4th. X double prime would be 20t cubed. And then y prime is 12t cubed minus 6t squared. And y double prime is 36t squared minus 12t. So that's my acceleration vector right there. This right here is a of t at any time t. And then if I want it at 1 second, I do acceleration at 1, and I get this amount here. Now the next example is just a little bit more involved than the others because it asks for the questions whose formulas are more complicated. I want the magnitude of the velocity vector, which is the same thing as finding the speed, meaning I'm going to end up with a number. And then I also asked for the total distance traveled from 0 to 5 seconds. So notice here we have formulas for total distance traveled, and we also have a formula for speed. Now, one thing that I want you to remember is you already know how to find the equation for arc length, or length of a curve. It was 1 plus f prime of x squared dx. It's been a long time since you did this, but if you had some curve, you could find the exact length of it with this formula. Notice this is the exact same, well, almost the exact same as this. This is just the parametric version of it. You have to have dy dt in addition to dx dt. Very similar to one another. And another thing I want you to notice, which I will show you here, is this right here gives me distance, and this right here gives me speed, the magnitude of velocity. These absolute value looking bars mean magnitude. If I wanted to go from distance to something talking about velocity or speed, I would do the derivative, because the derivative of position is velocity / speed. If I do the derivative on this side and the derivative on this side, well, derivative of distance is something having to do with velocity. Derivative of an integral is FTC part 2. The derivative and integral cancel, leaving me with this right here, which is the exact formula that I'm going to use to find speed. So let's go ahead and do speed first. I want the velocity here. That'd be the square root of dx dt, which I already found. So dx dt squared plus dy dt up here, squared. Now I want the speed at 5 seconds. So that'd be the square root of 2 times 5 squared plus 3 times 5 squared squared. Now I just noticed here, this should actually be a 2, because 3 times 2/3 is 2. So let's put a 2 everywhere where I had a 3. So anyway, this is going to be 2 times 5 is 10, 100. Plus 25, 50, 50 squared is 2,500. So the velocity, or I'm sorry, the speed is square root of 2,600, which is a number. Now let's find the total distance traveled. So now I'm going to do an integral from 0 to 5 of the square root of dx dt plus dy dt. So sometimes you can do this by hand. Usually, remember, these are kind of tricky to integrate. Usually you have to type into a calculator, which I will do. Now just keep in mind, if you had to do this by hand, it would be possible if you simplified this and factored out the common factor here and actually did the square root of it. You could do u sub and let this be u. Your final answer will be this, which if you wanted to get as a decimal, you could type into a calculator. But this is the total distance traveled. Now, I'm not going to go into the details of the u sub because this video is on parametric and vector, not on u sub. So if you want to verify that, those details can be for you. For the last example, I'll show you how to find when a particle is at rest. So we're going to use the fact here that if both dx dt and dy dt are 0, the particle is not moving. So let's go ahead and find dx dt. Now, make sure you're comfortable with both of these ways of writing it, dx dt and x prime of t, dy dt, and y prime of t. Both of those you should be good with. So what I did is I found the derivative here with respect to time of x and y. I factored 3's out of both to make it easier to factor. Now you set it equal to 0, and whenever you factor each of these, you need to see where the values agree, because it has to be 0 for both of them. So I have t equals 3 and negative 2 is when dx dt is 0, and t equals 3 and 1 is when dy dt is 0. So the particle is at rest at 3 because it's when both dy dt and dx dt are 0. So we'll practice this a lot on Monday and Wednesday, and then we'll move to polar. Have a great weekend.